Welcome. We will discuss about the coal-based DR process in this lecture. So, we will basically discuss the rotary kiln processes, okay, and so in details we will discuss about the process of rotary kiln, and then we will discuss about the rotary hearth furnace based processes, because these are the two processes which are very prominent today. Now, this is the flow sheet of the rotary kiln process. So, you can see this rotary kiln process in any textbook, you can find it. You can see the iron ore and coal and limestone. Limestone is very much important because to arrest the sulfur, limestone is used. Otherwise, it reports to the DRI. Okay. So, if you take the limestone, limestone basically has a capacity of absorbing the sulfur very much. So, iron ore, coal and the limestone are the feed. Okay, then it is, you can see directly coming. This coal is basically the reduction coal that is coming along with the iron ore. Iron ore basically in the form of lumpy ore is used, or sometimes you can use in the form of pellets also, but that become costly. Usually the lumpy ore, non-coking coal, limestone is coming like this. So, this is the feed, and you can see air and coal from the exit end. So, there is the coal burner here through which the air and coal passes through it, and then it produces the heat here. So, heating is done in the, and whatever you can find this port are the secondary, basically ports are there through the secondary air are coming here. This air is used basically for post combustion of the CO, because this direct reduction generates a lot of CO, and that CO when it is coming out and they are post combusted by this secondary air, okay, and that generates the heats also. And then you can find after the DRI is produced, is come through a rotary cooler. It is the indirect heating of the sponge iron by water spray on the indirect heating. It's not direct heating, because water sprays on the wall of the rotary cooler, and then this gas. Rotary cooler, basically the surface of the coal gets renewed, so it gets cooling first. And then this comes here, and then the screening, magnetic separation, and then you get the sponge iron. And whatever you can find, there is the waste gas. There is the whether it is the dust laden huge waste gas, and there is the dust laden waste gas come through it, and then you cool it, and then not only that, scrub the dust, and then electrostatic precipitator is also required to find out the fine dust, and then you can go to the waste gas. And this waste gas is also very rich in energy, so you can utilize it for the power generation and all these things, and the dust should be discarded. So, this type of cleaning system must be in place for a sustainable rotary kiln process. Now, this thing, so here some of the points I will mention if I forgot while talking about it. That is, the coal acts as both as a reductant as well as heat producer. You must understand there is the coal, it is coming at as the reductant here through this end feed end, and from the exit end you can find there the whole coal is coming, and here the coal is used only for heat generation in the burner. Okay, coal is burned in presence of iron and producing the heat. So, it is the coal that acts as a reductant as well as heat producer. No external heating is here. Operates on counter current principle. Here you can see the hot gas move in this direction, and the feed is coming from this direction. So, that is, there is a counter current, but here the gas is not moving through the solid, unlike in the shaft furnace where the gas moves through the solid bed. As a result, the interaction become much more. Here the gas is moving over bed, and the solid is going, there is the solid is going in this direction, gas is moving, but the gas is moving over the bed. Obviously, this is there. And the secondary air for the post combustion of CO, as I said, from the reduction, whatever the CO is generated is post combusted here by secondary air, and that generates the heat and supplement some of the heat required for the process. Waste gas cleaning system to reduce the pollution, as I said, it is very essential. Okay, so you have to discard the dust, and then the waste gas, a clean waste gas has to come out. Okay, so waste gas cleaning system to reduce the pollution to dust, because this rotary kiln process generates a lot of exit gas, and it contains a lot of dust. Obviously, it is a coal burners, okay. And waste heat recovery through the steam generation. Now, the waste gas that is coming out, as we will see, around 30 to 40% heat energy is carried through the waste gas. But chemical heat is there, a lot of CO there. So, therefore, you have to utilize that heat for generation, steam generation, and the power plant or the power generation. You have to utilize it. Otherwise, this process may not be sustainable. And then kiln rotation. Now, as I said, when the feed is coming in and the kiln is inclined to some extent for gravity, such that gravity the solid move from one end to the another. And the thing is that kiln is rotated. Why this rotation? If this rotate, then basically the surface of the coal gets, the surface of the raw material get renewed every time, both with respect to the wall, because the heat is coming through the wall also, because through the wall heat is coming to the solid, okay. That's why every time if it rotates, then the surface of the burden material with the wall also get renewed. As a result, heat transfer become efficient from the well to the solid wall solid, okay. So that way it is that is the thing. So kiln rotation refreshes the solid surface for efficient heat transfer into the solid, right. It is very important point. There is a rotation parameter and inclination of the kiln should be adjusted to avoid the fine segregation to the wall, because you can see when you are charging the raw material, the sizes are not uniform. There is a distribution of size. Besides, when this burden is physically moving through the kiln, they also generate fines, okay. So initially also there will be size distribution, so fines are there, coarse fines both are there, and during the transport or during the movement of the solid burden also some fines are generated. So as a result, and since it is rotating, so there is a chance of size segregation. That is, the fines will try to stick to the wall and the coarser particle will try to move towards the free surface, okay. So that tendency is there. So that you can reduce by controlling the rotation parameters and inclination of the kiln. So this is very important, because if the fines segregate on the walls, they will fuse, because wall is the very hot, and they will fuse also, because the fines contains a lot of gangue material is obviously there. So if the fusion point of the slag or the ash content of the gangue that is the exceeds, in that case the ash can melt and it can form the what is called accretion formation. So they can form the agglomerates on the wall, and then when the agglomerates grow and grow, they form a big agglomerate, and then they basically restrict the movement of the solid burden through the rotary kiln. That is called the accretion formation. So this is very important. So rotation parameter inclination of the kiln should be adjusted to avoid the fine segregation at the wall, basically to avoid the accretion formation. If the fines segregate at the walls and their fusion temperature exceeds, and then they can melt and they can generate the agglomerates and then develops into accretion. Indirect water cooling of DRI to avoid the reoxidation. You can see when the sponger is coming, we do the indirect cooling, because obviously you cannot directly quench the DRI, then it will be reoxidized. So indirectly you are cooling it. Then magnetic separation is done basically to separate the gangue material because gangue material will not respond to the magnetic field, where it is the metallized iron that will respond. As a result, metallized irons will be separated from the gangue. And some fine coal is also added at the dischargent to complete the reduction. So complete the reduction, fine coals if you give that the surface area will be higher. So whatever the reduction is pending, you can carry out at a much faster rate. Okay, so that's why that's there. So phenomena that is inside the rotary kiln You can see here, this is the cross section of the rotary kiln. Here only the solid burden, and the freeboard you can find, this is all vacant place at the freeboard. Okay. So only 15% loading, solid loading is there. So the solid charge constitute only 15% of the total volume, because you have to have 85% is free, because you have a dust laden gas, huge dust laden gas. You have to allow the space for the gas to move. Okay, you cannot charge it to a very higher extent. Solid charge, if you want to productivity, I will charge more solid, it is not possible. In that case, metallization will also be not good, because heat transfer take place from the surface to the solid, and also from the, not only that, surface to the solid as well as from here to here, from the furnace to the solid also. But if your charge is very large, in that case your heating will not be very good, because the heat will transport it from here to here, either here to here or here to here. So that to the core of the solid it has to penetrate. So if it is higher amount of solid you take, the core of the solid may not get sufficient heat. So metallization will not be high. This is one point. Second point is that this is the dust laden gas. You have a huge dust laden gas. You have to allow the space for that thing. Gas temperature in the freeboard is attained 1100 degrees centigrade. You can see this post combustion, all these things are taking place. So temperature become very high at 1100 degrees centigrade. Temperature in the solid bed should not exceed 1050. As I said, in the solid bed inside it should not exceed 1050, because if it is very high temperature, then incipient fusion of the ash will increase the propensity for the formation of the accretion. So high reactive coal allows gasification reaction and restricts the solid temperature beyond 1050. So what you can do, sometimes you can use some coal with a high reactivity such that the gasification reaction inside the solid bed moves at a faster rate. And gasification reaction is endothermic, that will basically control the temperature of the solid bed. That is one way of doing it. Submerged controlled air injection to facilitate the preheating and in situ CO generation in the solid. So you can see there is a submerged air injection facilities are there. So these air basically inside, it gives rise to some kind of oxidation of the carbon, giving rise some heat, and also helps in situ generation of the CO. Okay. So it helps basically in the preheating and the CO generation, making the process faster. So these are some improvement, that is the air injection, submerged air injection from the bottom of the bed. So this is about the phenomenon. Now salient features, some of the salient features of the coal based rotary kiln DR process. One thing is that flexibility with regard to the type of iron bearing material. Flexibility is there, which can be used, such as you can use the lump ore, you can use pellets, you can use directly low grade iron ore, there is the ilmenite, iron sands you can use, and the steel plant waste also you can use in the agglomerated form obviously. So you can directly use, so there is a flexibility with reference to the iron bearing material. And you can use wide variety of solid fuels also, starting from anthracite to the lignite, non-coking coal obviously. And use of lignite is good, because lignite is very reactive. That is the one thing, is that lignite is very reactive. Sometimes it is too reactive. You have to decrease this reactivity to some extent using. So since lignite is reactive, you can operate the furnace at comparatively lower temperature. That is one way. It's good. But its fixed carbon content is less. That's why you have to mix it with some good grade of coal, such that you can maintain a balance between the reactivity and the fixed carbon. Okay. Otherwise, the non-coking coal is also used, but you can use a wide range of coking coal with an optimization amount. Just I have talked about that. There is the submerged air injection. Optimized coal injection facility, that is also available. That is the how much coal you will inject, you can optimize it. I have talked about lot of direct reduction process variants. okay, all patented process, and these are some of them. There is optimized cool injection facility is one of them. This is very important, waste gas conditioning by control post combustion. That is, you are doing the post combustion for extra heat generation inside the kiln, such that you can reduce the coal from the feed end. Okay. So that is the in the burner, there is the coal in the burner, you can reduce some amount of the coal in the burner by using the post combustion. You are generating some extra heat. Now the waste gas conditioning is that whatever the waste gas that is coming, and if you are using it for the power generation, then you know what is the requirement of the CO in the waste gas. So to maintain that waste gas CO requirement, you can control the post combustion. That is, you may not do too much of post combustion. Sometimes if the CO is more into the waste gas, you can do more post combustion. If the CO gas requirement for the power generation is less in the waste gas, you can do less post combustion. So you can waste gas conditioning you can do by controlled post combustion operation. That obviously the secondary air you can control it. That I said, there is a waste gas heat recovery by steam generation. I think it should be done in all the cases. The Lurgi, Germany, there is the SLRN process. That was the SLRN process, is a rotary kiln furnace based DR process, and it was invented by, it belongs to the Lurgi, Germany, Lurgi company, Germany. Okay, and it is the oldest and most widely applied rotary kiln furnace, the rotary kiln based DR process. Other process like German Coedid, as there I have talked about, Canadian, there is the Alice Chalmers controlled atmosphere reduction process, and the process also uses natural gas and oil in addition to the coal, as I said. As a result, you can control the carbon content into the DRI. Canadian DRC process is there, and the TDR TISCO direct reduction process, and it ensures the proper reducing condition along the entire length of the kiln. Some process variant. Jindal process claims any inferior grades of ore can be converted to sponge with 90% metallization. Now, I will talk about some of the strengths of the coal based rotary kiln DR process. So what are the strength? Efficient mixing of solid charge during simultaneous heating and reduction. So efficient mixing is there because of rotating, as I said, the solid charge gets renewed every time, surface of the solid charge. So that basically gives the efficient mixing of the solid charge, and also for heat transfer and for all chemical reaction, heating and reduction. That I said, that is the large freeboard basically can handle a heavily dust laden gases. But in case of the shaft furnace, you cannot use this much of dust laden gas, cannot be operated in a shaft furnace because that will choke the shaft furnace and process will be abandoned. So using the low, that is the heat generation by the non-coking coal itself, okay, it cannot be done into the shaft furnace. In the rotary kiln only, you can generate the heat from a low grade, inferior grade of coal. You can use that coal as a reductant both, because you have the reactor has the facility, it can handle a large amount of dust laden gas. There is a reactor, that's why that type of reactor, rotary kiln reactor, is good for that coal based process. So rotary kiln process acts as both an efficient gas, there is the coal gasifier as well as ore reducer. Both the things in the same reactor, both the coal gasification taking place as well as it acts as an ore reducer. It serves a dual purpose. They are commercially proven, very rugged reactors, and it was extensively used into the cement industry. It has little low productivity, but it is more than compensated by its inherent versatility. Because it has versatility, it is rugged, very versatile. You can use different grades of raw material. So those point of view, it is Now, I will give you an example of energy balance in the rotary kiln process. You can see input energy around 5.7 to 5.8, that is the gigacalorie per ton of DRI. Okay, it is all in terms of gigacalorie. Okay, gigacalorie. So input energy is 5.7 to 5.8, and it is through the coal only. So measured energy input through the coal. Okay, and this is the recirculating heat, point 1, because the coal is the reductant, coal is the energy producer. So coal is the all, that is why the major energy is coming by the coal only, that is 5.7 to 5.8, and some recirculatory heat, some sensible heat you can recirculate. Okay, so output energy, if you see sponge iron contains around 35% of the total heat goes to the sponge iron, 1.75 to 1.8 gigacalorie per ton of DRI. Then char, that is the coal char, contains significant amount of energy, 1.1 gigacalorie goes into the char. Char means there is the whatever the reduction coal you are giving, they are first devolatilized, and then the char reacts in the carbon gasification reaction also, and some amount of the char is left out, that comes out along with the sponge. So that char contains significant amount of energy, that is 1.1 gigacalorie. Waste gas loss significant, 2 gigacalorie per ton of DRI, that is around 40% of the total heat. That the majority of the total heat goes at waste, 35% remains into the sponge iron, 1.1 that is around in the char, and the 40% of the total heat goes to the waste. Cooling loss 0.25, unaccounted 0.6, it makes it equal. So you can see 40% of the total heat goes to the waste. So energy in the waste gas is significant, must be recovered to make the process economical and sustainable. Typically 1 lakh ton per annum rotary kiln produces around 80,000 meter cube of waste gas at a temperature of 1000 degrees centigrade. Okay. So this is the sensible heat, you can guess the sensible heat. Besides, it contains a lot of CO, so that also gives the chemical heat. So, and these combined, they can produce around 7.5 megawatt electricity, and 1.5 lakhs ton per annum kiln, it can be around 10 megawatt, and 70% of it will be surplus even after using into the plant. Okay, you can sell it. So this is the overall balance. So you can understand from this balance, that is the waste heat law. Waste gas contains a significant amount of energy, around 40% of the energy of input energy. So it must be used to power generation. Otherwise, this process will not be sustainable. Drawbacks of the rotary kiln process: productivity is low, and shaft furnace have 5 times more output per unit volume. That productivity is low. Shaft furnace has much higher productivity, 5 times more output. Large capacity DR plants have to incorporate multiple rotary kiln. As I said, one rotary kiln capacity is only 5 tons per day, 500 tons per day. So if you want to make a higher capacity, say 2000 tons per day, if you want to produce, you have to apply 4 rotary kiln. Okay. So that basically increases the specific energy consumption, although the investment cost may be less initial. Gives rise to interference and complexity in large plants. Reactor rotates at 0.4 to 0.5 RPM, making it difficult to incorporate the process control and quality control system. That is there. Process control, that is, if you want to measure the temperature also, if you want to put the thermocouple, it's difficult because it is rotating. So instrumentation of such furnace become little difficult because it is rotating. So the quality control system also suffers. So engineering of rotary kiln fairly intensive because of rotation and length and diameter of the reactor, considering all these factors. So as I said, it doesn't show very high efficiency. Around 40% of energy reports to the waste gas. So waste gas you have to utilize. Another very major problem of the rotary kiln furnace is that dust laden waste gas. So you have a dust laden waste gas that has to be utilized properly, because otherwise it pollutes the atmosphere significantly and not at all sustainable. So whatever the dust that is coming out, you have to clean the dust. You have to use the scrubber, you have to use the electrostatic precipitator, and then finally the gas has to be dust free. And then that gas will go to the power plant, and then the waste gas will join the atmosphere. So dust should not be allowed to leave to the atmosphere. Accretion formation is the major problem in the rotary kiln process. Repeated rotation results in size separation, as I said, size segregation. As the charge moves forward towards the discharging gate, there is a size segregation. So fines try to accumulate on the wall and the coarse on the free surface. So this is the, so as I said, when the fines accumulate on the surface, as I said, and when the ash of the iron ore, there is the fine iron ores, exceeds when they achieve the ash fusion temperature, they basically melts, and then they try to form agglomerate on the surface of the wall, and then they basically grow over time. And finally, this type of accretion can form. You can see almost all the cross section of the tunnel is blocked by the accretion. These are things I have talked about. So as I said, what are the remedy? Remedy is that one thing, as I said, you can control the operating parameters as well as the inclination of the rotary kiln such that the size segregation become limited. And second thing is the reactive coal. If you use the reactive coal, then you can increase the carbon gasification reaction. And since carbon gasification reaction is highly endothermic, you can reduce the solid bed temperature significantly. So you can carry out this process around less than 1050 degrees centigrade. So your accretion formation tendency will be less. And this ring basically consists of, that is, the alumina silica from the coal ash, the CO from the flux, and the FeO from the sponge iron. So this basically, they form low melting eutectics. Okay, so they can, their fusion temperature can exceed even at 1050 degrees centigrade. Easily it exceeds, and that's why they basically form this mass, agglomerated mass. Okay, so this is about the basically rotary kiln process, and I will stop here and I will continue in the next lecture.